A little bit about some of the generations of CT scanners, and I'm going to go through some of these fairly briefly and spend a little bit more time on others. So the first scanner, when Sir Godfrey Hounsfield made his first scanner, it had a parallel ray geometry. You basically had a pencil beam of X-ray, so a single X-ray beam, if you will, and it went in that single X-ray beam, shined a line through your object and hit this detector, and that intensity was measured. And then it translated over a little bit and it repeated that process. So we measured a single line of projection data, just a single line at a time. And then once we translated all the way through, we rotated and did that again, right? So this is like me showing you those simple back projection images, right? Only it takes forever to get each one of these images. 4.5 minutes to scan one slice, and that's only getting 160 rays in each slice and going 1 degree apart before we repeated. And the reconstruction took about 1.5 minutes. So we did this: translate to acquire each line, rotate, and then start the process all over again. And there's his setup. The funny thing was, he actually had a detector sitting below this one in the Z direction. So the first scanner was, if you will, a multi-row detector scanner, right, consisting of 2 rows. So the second generation simplified the problem by saying, hey, let's have, rather than a pencil beam, let's have a fan beam of a small number of rays, 4 or 5 of them or so, and that'll decrease the number of translations that we need to do. Now, some people thought, well, that's a little bit problematic in that each of these is now traveling straight across. It's at a slight angle. But it turns out if you limit that to just a few, 4 or 5 or so, the approximation that they were about the same as the parallel lines that we would get in the translation is close enough that this still works out very nicely. And using this, notice they were able to speed things up a little bit, right? Now we could do about 18 seconds to scan one slice or so. So in the third generation, we got rid of that translation need, right? We increased the number of detectors to around the 750, 800 that it is today. They're all located on a kind of a curved surface in kind of a fan configuration. It's enough to kind of give you the entire patient can be included in the field of view. And then we joined the tube and the detector together mechanically, so now we could just basically rotate. There was no need for the translation motion. All the mathematics that had been developed to do reconstruction using filtered back projection assumed that the acquired projections were parallel to each other. But now does everyone see, right, we're acquiring this broad fan type projection. And so one of the things that had to happen in order to go from this parallel beam projection process, which was quite slow, to this fan beam acquisition was the realization that you had the same data sets. It's just that they were organized completely differently. And I want to show that to you by showing you this picture. Does everyone see, here I've got 2 positions where we've done our fan beam acquisition, a few degrees apart from us. We've rotated over a little bit here to get the one that I've labeled in blue compared to yellow. Now I'm going to start to subtract some of the rays from this, some of the projection lines away from both of these, okay? So let's start to subtract some of those out. And does everyone see that there are a pair of lines in these 2 projections which are parallel to each other? And if you rotate entirely around the body, if I did this at a 3rd spot and color-coded that red, I could keep one of my red lines, which was parallel to these ones. And if I did that at the next position, there would be. And so really all you needed to do was take the fan data and do what we call rebin it, resort it, into all the rays that were parallel to each other, and then do your filtered back projection on that. So it took that kind of leap of faith. And really, this is what our modern scanners do, with one exception. At some point, we decided we were going to move the X-ray table while we were rotating. We were going to go to a helical acquisition or a spiral acquisition. But before that happened, a couple of other things were introduced. Here was the 4th generation CT. You just made a complete row of detectors. This is nice because when I showed you that rotating gantry, you know, the detector and the X-ray tube in combination that are rotating, they're way over 2,000 pounds. We certainly don't tell the patient that when we, you know, put them in the bore of the scanner and rotate it 3 times a second, right? So if I no longer have to rotate the detector and can just rotate the tube, I can get the speed of that rotation a bit higher. I've got less mass that I'm having to rotate around. But what did I tell you about the detectors? They're the most expensive part of the CT scanner, right? So the problem with this is, rather than having 72 degrees of detectors, you've now got 360 degrees of detectors you have to pay for. So that kind of fell by the wayside. Here was the 5th generation of scanners. This was electron beam tomography, where now I bring my electrons in and I actually fire them to strike these targeting rings, and I can steer them. These targeting rings actually go around the patient 180 degrees, and I can steer my electrons to go hit them at different points. So now in electron beam tomography, I didn't even have to rotate an X-ray tube around the patient. And this was popular for a while in kind of the mid-90s because you could do a very fast acquisition with this. So for cardiac imaging, it was really the first scanner that was utilized for doing that. But again, it's extremely expensive. And so this really got replaced with this 6th generation of CT, helical or spiral CT. You know, those previous scanners operated in sequence mode. In other words, the X-ray tube and detector rotated 360 degrees around the patient, then they stopped. The table shifted forward a small increment, then they rotated back the other direction. Table shifted forward again, they rotated in the other direction, and then continued to do that. And part of the reason for that was you had these really heavy-duty power cables connecting to the X-ray tube and connecting to the detectors, although those don't have to be the same kind of power requirements. And so you couldn't continue to just rotate the tube in one direction. If you did, you'd wind those cables up and rip them apart. So someone had to come up with a way to allow that to continuously spin, but still maintain high quality, high power electrical connections with those devices. And that's the slip ring technology that we see today. So here's the old, right, just continue to rotate and move the table forward, which is what the tube did. It only did that on the older versions, right, rotated 360. Then the table shifted in an increment. Now we're going to move the table continuously while the tube continues to rotate, and we end up tracing this kind of helical path, if you will, of X-ray energy through the patient. Here's that technology that had to exist in order to make that happen. Does everyone see this big center cylinder of metal that's here? And these are the electrical connections. They're actually little pads that fit in these grooves here. And I'm going to show you those up close. Well, here it is up close, and here's stepping further back away from that. So these are all the electrical contacts that are made through there. And they're made with this device. You can see that this is almost like a coil spring, right, that you might see on an old car suspension, right? And so it forces them up to maintain contact with those rings. So that slip ring technology allowed you to maintain contact with that moving portion of the scanner without having cables directly connected to it. The 7th generation just now added multiple rows to the detectors, right? We first had single row helical scanners. Now we started to look at multi-row detector helical scanners. And you know, there are some more issues. We talked about the interpolation problems with fan beam. Now we've got helical scanners, so the data that we acquire isn't all exactly in that one slice like it would be for the sequence acquisition, right? And so you can't move the table as fast as you might like to move it. If you move it too fast, your reconstruction quality is going to suffer from that. And we'll talk a little bit about that when we talk about the concept of pitch. But when we added multiple rows to the scanner, it allowed us to travel the Z distance that we traveled per one rotation of the scanner got greater. And so we could scan through the patients even quicker with that generation. So here we are looking, we've got our individual detectors in any one given row. I've already mentioned the fact there's about 750 of these that span a 72-degree arc. And then the first scanners started out with 2 rows, and then quickly we went to 4, and then this is happening while I was a resident in the early 2000s. So the next thing I know, we have a 16-row detector scanner, and the next thing I know, we have a 64-row detector scanner, and then a 128, and now there are scanners, that have many more than that. So here's the Siemens volume zoom, the 4